Forget the intro, here it is. Number 8. Complex molecules where none belong. At a redshift of 8.3, meaning its light has been stretched so far by the expanding universe that we are seeing it as it was over 13 billion years ago, the James Webb Space Telescope detected a galaxy producing stars at 180 times the rate of the Milky Way. That alone is unusual, but the chemical fingerprint of that light revealed something far stranger: carbon signatures, oxygen, complex organic compounds frozen in ice around a young star in a neighboring galaxy, including molecules never before detected outside our own Milky Way. The models are specific about this. In the first billion years after the Big Bang, the universe contained almost nothing but hydrogen and helium. Heavier elements, the carbon and oxygen and nitrogen that make chemistry possible, those required generations of stars to live and die. Massive stars had to burn through their fuel, explode as supernovae, giant stellar explosions, and scatter their guts across space. Only then could the next generation of stars and planets inherit those elements. This process takes hundreds of millions of years at minimum. The first cycle alone requires at least 50 million years just for the gas to cool after the initial supernovae. The telescope found those heavy elements already present, already abundant, already frozen into molecular ices at a time when the first generation of stars should have barely finished dying. The chemistry was running ahead of the clock, not by a small margin, by hundreds of millions of years. You are looking at a universe that built complexity before it had the tools to do so. Either the first stars burned hotter and died faster than any model predicts, or there is a mechanism for producing heavy elements that we have never identified. Impossible molecules were strange, but at least we could classify them. This next one we cannot even name. Number 7. 300 objects that defy classification. Astronomers at the University of Missouri pointed the James Webb Space Telescope at a patch of deep space and found 300 objects that were brighter than anything at their distance has any right to be. These are not galaxies behaving strangely. These are not quasars, those intensely bright objects powered by black holes devouring everything around them with unusual properties. These are objects that do not fit into any existing category. Every model of the early universe provides a ceiling for how bright an object can be at a given distance. Brightness correlates with mass. Mass correlates with age. Age correlates with how long gravity has had to pull matter together. There is a budget, and these 300 objects are wildly over it. Some researchers proposed they were galaxies with active supermassive black holes at their centers, the accretion disks, the swirling rings of superheated gas being pulled into the black hole, inflating their apparent brightness. Others suggested they were a new class of object altogether, something called little red dots that the telescope keeps finding in the ancient universe. Compact, intensely luminous, red, and small, not matching any template astronomers have ever used. The telescope found 300 of them in a single survey, not one anomaly, not a handful of outliers, 300 violations of the brightness ceiling, scattered across the early universe like evidence of a rule that never existed. You are not watching a model get refined. You are watching a classification system fail. 300 unclassifiable objects was a problem. A star older than the universe is a contradiction. Number 6. A star older than the universe. HD 140283 sits 200 light-years from Earth in the constellation Libra. You can see it with binoculars. It moves across the sky at 800,000 miles per hour, a visitor from the ancient halo of stars that surrounds the Milky Way. Astronomers have studied it for over a century, and in 2025, an astroseismic analysis, a technique that measures a star's age by studying its internal vibrations the way a doctor listens to a heartbeat, measured its age at 14.2 billion years, with an uncertainty of just 400 million years. The universe is 13.8 billion years old. That number comes from the cosmic microwave background, the faint afterglow of the Big Bang itself, along with the Planck satellite data, the expansion rate, and every major cosmological measurement of the last 3 decades. It is one of the most precisely known values in all of physics. The Methuselah star, as it is known, predates its own container. The best measurement of the star's age places it 400 million years before the Big Bang. The error bars overlap, barely, but the central estimate does not lie inside the age of the universe, it lies outside it. Previous estimates ranged from 12 billion to 16 billion years. The measurements have narrowed, not widened, and as they narrow, the star's age is not converging on a comfortable number. It is converging on an uncomfortable one. You do not need to understand stellar physics to feel what this means. There is a star in the night sky that is, by our best measurements, older than everything. Number 5. A galaxy that should not exist at 280 million years. MOM-Z14 was observed as it appeared just 280 million years after the Big Bang. The models were explicit about what should exist at that age: small clumps of gas, faint smears of light, chemically primitive structures still assembling themselves from hydrogen and helium. Instead, MOM-Z14 is luminous, structured, and contains elevated levels of nitrogen. Nitrogen requires multiple generations of massive stars to produce. Each generation needs to live, burn its fuel, explode, enrich the surrounding gas, and wait for that gas to cool and collapse into new stars. The timescale for this process, repeated enough times to build nitrogen abundance, is measured in billions of years. The universe at 280 million years had not provided those billions of years. It had provided 280 million, and the galaxy was already chemically mature. In the same survey, astronomers confirmed JADES-ID1, the most distant galaxy protocluster ever found. A protocluster is not a single galaxy forming in isolation. It is a cluster of galaxies already assembling into a larger structure. The universe was building cities before it had finished laying foundations. These are not edge cases. The telescope keeps finding them. Mature structures where chaos should reign. Order where there should be nothing but potential. The universe was in a hurry to grow up, and nobody told physics. Galaxies forming too fast is one thing, but the black holes inside them are an even bigger problem. Number 4. Supermassive black holes at cosmic dawn. The quasar J1120 plus 0641, a galaxy with a violently active black hole at its core, sits 13 billion light-years away. The James Webb Space Telescope observed it in mid-infrared for the first time, analyzing the spectrum of light from a supermassive black hole that existed when the universe was only 770 million years old. Its mass is over 1 billion times that of the Sun. Black holes grow by consuming matter. Matter spiraling into a black hole forms an accretion disk, a swirling ring of gas heated to millions of degrees. That disk radiates energy, and that radiation pushes incoming matter away. This sets a speed limit. Physicists call it the Eddington limit, the fastest rate at which a black hole can eat. A black hole feeding at that maximum, eating as fast as physics permits, would need roughly 1 billion years to reach 1 billion solar masses. The universe at 770 million years old had not provided 1 billion years of feeding time. But the black hole was already there, already massive. And when the telescope examined its accretion disk and the thick donut of dust and gas surrounding it, it found something that made the problem worse. The feeding mechanism looked normal, ordinary, the same as black holes billions of years younger. No evidence of some exotic ultra-efficient mode. No sign of abnormal consumption. The black hole was not eating fast. It was just already enormous. Across dozens of early galaxies, the pattern repeats. Supermassive black holes constituting 1 to 10% of their host galaxy's total mass, compared to the 0.1% ratio observed in the modern universe. These black holes are 10 to 100 times more massive than they should be relative to the galaxies around them. As one astrophysicist put it, it is like looking at a 5-year-old who is 6 feet 6 inches tall. Something does not add up. Either black holes were born massive, collapsing directly from enormous gas clouds without ever being stars first, or our understanding of gravity, accretion, and time is incomplete. Neither option is comforting. Number 3. Galaxies that died before most galaxies were born. The James Webb Space Telescope found galaxies that stopped forming stars more than 13 billion years ago. These are not old galaxies winding down at the end of long lives. These are galaxies that burned through their entire gas supply in the first few 100 million years of cosmic history, formed all the stars they would ever form, and went dark. The standard model of galaxy evolution describes a gradual process. Galaxies form stars over billions of years, slowly converting gas into stellar populations. Some eventually exhaust their fuel or have it stripped away by interactions with other galaxies, but this process takes time. A galaxy dying within the first billion years of the universe is like a human reaching old age before their first birthday. These dead galaxies are chemically rich, structurally mature, and completely inert. They lived fast, and they died young. And they did it at a time when the universe should have been nothing but a nursery. The implication is that star formation in the early universe was not gradual. It was catastrophic, orders of magnitude more violent than anything happening today. Galaxies were not gently assembling themselves. They were detonating into existence and burning out. Number 2. The universe expands at 2 different speeds. For nearly a decade, astronomers have measured the expansion rate of the universe using 2 independent methods and gotten 2 incompatible answers. This discrepancy is called the Hubble tension, and the James Webb Space Telescope was supposed to resolve it. It did the opposite. The cosmic microwave background, the afterglow of the Big Bang mapped by the Planck satellite, predicts the universe should be expanding at 67.4 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years, so this number tells you how much faster distant objects are flying away from us the farther out you look. Measurements of supernovae and Cepheid variable stars, pulsating stars that brighten and dim at predictable rates, allowing astronomers to measure cosmic distances, consistently produce a value around 73 kilometers per second per megaparsec. The gap between these numbers is roughly 9%. The hope was that Hubble's measurements were slightly wrong. Distant stars crowded together, dust dimming the light, subtle errors compounding over billions of light years. The James Webb Space Telescope has 4 times the resolution of Hubble and 10 times the sensitivity. It observed the same Cepheid stars, the same galaxies, the same supernovae, and the measurements matched Hubble's data almost exactly. A value of 72.6 kilometers per second per megaparsec from Webb compared to 72.8 from Hubble. The difference is under 2%. The measurement error is gone. The tension remains. The universe is expanding at one speed when you calculate forward from the Big Bang, and a different speed when you measure it directly. Both methods are verified. Both are precise, and they disagree. Either the standard model of cosmology is missing a component, something like early dark energy, a mysterious force that pushes space apart, giving the universe an unexpected kick after the Big Bang, or the fabric of space-time behaves differently than Einstein's theory of general relativity predicts. Either way, the math that governs the age, size, and fate of the universe does not close. You are living in a universe that cannot agree with itself about how fast it is growing. Number 1. The cosmic web is wrong. In January 2026, researchers published the most detailed, high-resolution map of dark matter ever produced, using James Webb data to peer 8 to 11 billion years into the past. Dark matter is invisible. It does not emit light, it does not reflect light, but it has gravity, and that gravity shapes everything we can see. They tracked nearly 800,000 galaxies in the constellation Sextans. The map reveals the cosmic web, the vast network of dark matter filaments that acts as the gravitational scaffolding for every galaxy, every cluster, every supercluster in existence. Think of it as the skeleton of the universe. Galaxies form along these filaments the way cities form along rivers. The map is twice as detailed as anything Hubble produced, and at the finest scales, it does not match the standard model. The lambda CDM model is the mathematical backbone of modern cosmology. It is the master equation that describes how the universe works, from the Big Bang to today. It predicts how dark matter should be distributed. It predicts the density of filaments, the sizes of voids, the clumpiness of the web at different epochs. This model has survived every test for over 2 decades. It is the closest thing cosmology has to a constitution. The new map reveals smaller-scale structures and a degree of clumpiness that the model does not predict. The dark matter is not distributed the way the math says it should be, not at these resolutions, not at these distances. The deviations are subtle, but they are real, and they are present across billions of light-years of cosmic history. Some theorists propose that dark matter interacts with neutrinos, ghostly subatomic particles that pass through everything, in ways the standard model does not account for. Others suggest the model itself is an approximation that breaks down at finer scales, the way Newtonian gravity works perfectly until it does not. This is not a galaxy that formed too early. This is not a star that is too old. This is the scaffolding of the universe itself behaving in a way that the foundational model of cosmology did not predict. The skeleton is wrong, and everything built on that skeleton, every galaxy, every void, every prediction about the future of the cosmos, inherits that error. You are not looking at an anomaly. You are looking at the floor shifting beneath the building. The universe is not hostile. It is not malicious. It is not trying to confuse you. It simply does not owe your models anything. It does not care what the equations predict. It does not ask permission before violating a law that took a century to write. Every one of these 8 discoveries says the same thing. The universe was here before your math, and it will be here after your math fails. The telescope did not find answers. It found the edges of what we are allowed to know, and those edges are closer than anyone expected. If you want to see more videos like this, click the video on the screen now.